5.2 Logarithmic functions and their graphs. We've taken a look at exponential functions in section 1, so now we're going to do the inverse, the logarithmic functions. By definition of logarithmic function with base a, for x greater than 0, a greater than 0, and a not equal to 1, if log base a of x is the same as x equal to a to the y. The function is given by, it's read log base a, so this is considered your base, and this is called a logarithmic function with base a. Here's how that's transferable. We've seen base a here where y is an exponent. Now a is still the base, but it's the base of a log, and what it's equal to is the exponent. So the equations y equals log base a of x and x equals a to the y are equivalent. The first equation is logarithmic form and the second is in exponential form. This is a skill that we're going to learn on how to start with a log and go to an exponent, and start with an exponent and go to a log. For example, the logarithmic equation 2 equals log base 3 of 9 can be rewritten as 9 equal to 3 squared. Here's how we can do this. If you take 2 equal to log base 3 of 9, here's how you can translate it. The base of your log, let me set up what I want here, is the base here. A log is equal to an exponent, meaning this is your exponent, so 2 would come here. The only number I haven't used is the 9, so then 9 would come out here. And you can see that this is a true statement. 3 squared is equal to 9. Same thing with this one. 5 cubed equals 125. I want to take that 5 cubed equal to 125 and rewrite it as a log. Here's my 3 boxes I have to fill. The base of your exponent becomes the base of your log. A logarithm is equal to an exponent. That's a phrase I'm going to say quite a bit. It's equal to an exponent, so the exponent becomes over here by itself, 3. The only number I haven't used is 125, so I would put it here. So when evaluating logarithms, remember that a logarithm is an exponent. We're going to use that phrase quite a bit. A logarithm is an exponent. This means that log base a of x is the exponent to which a must be raised to attain x. So here's how we can do it. Start with what you're given. Log base 2 of 8 equal to 3. Set up what you want. So I need 3 spots here. The base of my log is the base of my exponent. A logarithm is equal to an exponent. That means a log is equal, so 3 is the exponent. The only number I haven't used is 8, and I would put it here. Now you be sitting there thinking 2 cubed is equal to 8. Duh, teacher. Well, the reason is we need to learn this with something that we're familiar with, is so that we have values that are variables, we'll be able to solve them. So we're going to use the definition of a logarithmic function to evaluate each logarithm at the indicated value. Okay, so here's what we're going to do. We're going to take what we're given, plug it in, and see if we can get that value. So you can see in the first one, if I have y equal to log base 2 of x, and I want to use x to be 32, I'm going to plug in 32 here. Then I'm going to rewrite it so I can actually solve it. I'm going to say 2 to y equals 32. Well, 2 to what power would give me 32? The 5th power. So then I'm able to say that that log is equal to 5. Let's try the next one right here. So this says y is equal to log base 3 of 1. I'm taking this 1 and plug it in for x. Rewrite as an exponential. So the base of your log becomes the base of your exponent. A logarithm is equal to an exponent, so y is what goes up here. Equal to the number we haven't used, which is 1. Well, what power of 3 gives me 1, and that's the power of 0. So I could say 0 is what this log is equal to. next to. Now, so I'm going to say, some may say write as an exponential function. Others will just have you to solve. So you have to know how to convert from one to the other, either in simplest terms of it asking you to convert, or more complicated terms of actually having to convert it to solve. And so, if y is equal to log base 4 of 2, set up your boxes. So the base of your log becomes the base of your exponent. A log is equal to an exponent, meaning y goes up here and a 2 here. Well, what power of 4 would give me 2? Well, I'm going to have to reduce it somehow. So I know if I square root 4, that would give me 2. And square rooting is a 1/2 power. So what is this log equal to? 1/2. Here in this last one, y is equal to log base 10, this would be a good test question, of 1 over 100. So set up your boxes. The base of your log becomes the base of your exponent. A logarithm is equal to an exponent, so y goes here, and I haven't used 1 over 100. Well, if I'm getting a smaller number, that means I really have 1 over 10 to a negative y equal to 1 over 100. And then what power of 10 would give me 100? That would be a square term. And so that means that I'm going to need a square underneath here, therefore I'm working with negative 2. So what is this logarithm equal to? Negative 2. The logarithmic function with base 10 is called a common logarithmic function. It's denoted by log base 10 or simply by writing log. On most calculators, this function is denoted by just a log button. So if you were to see this button log on your calculator, it's referring to base 10. Typically, we don't write base 10. So the following properties follow directly from the definition. Write this down. Properties of log. Log base a of 1 is equal to 0, and that's because a to the 0 is 1. Log base a of a is equal to 1, and that's because if you rewrite it, a to the first is a. Log base a of a to the x equals x, so it's almost like this part cancels out to give you x. And same thing here, a log base a, those cancel each other, they're inverses, so you just get x, inverse property. And if log base a of x is equal to log base a of y, then x equals y, and this is your one-to-one property. Very crucial. We will work with this quite a bit. Now, graphs of logarithmic functions, let's look at what they look like. To sketch the graph of y equals a to the x, you can use the fact that the graphs of inverse functions are reflections of each other in the line y equals x. Now, there will be no graphing on this exam, but I do want you to know what the shapes look like in order to go through different activities. So in the same coordinate plane, we're going to sketch these two graphs here. 2 to the x, which we know kind of looks like this, and log base 2 to the x. Now it says that it would be a fraction over y equals x. So if I were to look at y equals x, it should reflect over that to give me something that looks like this. You can see it here in this nice little picture that for 2 to the x, we can construct a table to figure out what it looks like. And this is this one here. This is y equals 2 to the x. It is reflected of y equals x, this dotted line coming down here. And so then you can see here that log base 2 to the x is down below. Because g of x is equal to log base 2 to the x is the inverse function of f of x equal to 2 to the x, the graph of g is obtained by plotting the points and connecting them with a smooth curve. So the graph of g is a reflection of the graph of f in the line y equals x. So again, I'm not going to make you reproduce this, but I do want you to be aware of the facts and how this actually works out. So we looked at y equals 2 to the x earlier. So if we reflect it over this y equals x, we can get log base 2 to the x. The nature of the graph in figure 5.15 is typical of functions of the form f of x equals log base a to the x, where a is greater than 1. They have one x-intercept, one vertical asymptote, and notice how slowly the graph rises when x is greater than 1. So you can see how this is kind of reflective of the RE1 we're looking at. We still have an asymptote. We still have an x-intercept compared to a y-intercept in the inverse function. Things I would write down: the basic characteristics of a logarithmic graph are below. The domain is 0 to infinity. You can see that's the reverse of what we saw in the exponential function. The range this time is negative infinity to infinity. We have an x-intercept of 1, 0. It's increasing, and it's 1 to 1. Therefore, it has an inverse function. Graphs of logarithmic functions. Y-axis has a vertical asymptote. It's continuous, and it's a reflection of the graph y equals a to the x about the line y equals x. So, the basic characteristics of the graph of a to the x are shown below to illustrate the inverse relationship between g of x. The domain is negative infinity, it's 0 to infinity. You have this in your notes. Y-intercept 0 to 1. It has a horizontal asymptote. So let's move on and look at the natural logarithmic function. This inverse function is called the natural logarithmic function, and is denoted by the special symbol lnx, read as the natural log of x, or ln of x. Note that the natural logarithm is written without a base. The base is understood to be base e. So if we have one that says that it's log base e of x, more appropriately we just say ln x. The definition above implies that the natural logarithmic function and the natural exponential function are inverse functions of each other. So if you have y equals e to the x, the inverse function would be ln x equal to y. So every logarithmic equation can be written in an equivalent exponential form, and every exponential form can be written in logs. So that being said, it means you can go from a log to an exponent, and from an exponent to a log. That is, y equals ln x and x equals e to the y are equivalent equations. So excuse me, better letters would be x equal e to the y. And because the functions given by f of x and g of x are inverse, again, you can see that they are reflected over y equals x. This is the reflective property. On most calculators, the natural log is denoted by ln using its own button. So let's figure out and make sure we know how to use that button. So again, grab your handy dandy calculator. I would use your scientific one that you plan on using for most of this chapter so you become familiar with it. And we're going to kind of play around a little bit. So what if we find f of x equal to ln x for each value of x? So that means right here, I'm going to do y equal to ln of 2. So I'm going to go to my calculator and I'm going to type in ln button. It'll use open parentheses. I'm going to close it up with a 2 in there. See what you get. Again, go in here and equal yn of ln of 0.3. See what you get. Y equals ln of -1. See what you get. And y equals ln of open parentheses 1 plus the square root of 2, close parentheses. See what you get. Now let's compare answers. So if I plug in ln 2, you might have plugged in, ln of 2. You should have gotten 0.693, again 3 decimal places. ln of 0.3, I have to use parentheses on my calculator. Everyone's keystrokes are different. I had an older calculator using one time, and I would have to type 0.3 and then the ln button, and then it would tell me the value. So make sure you're playing around with it and getting these same answers. And this would give me negative 1.204 when I round appropriately. ln of -1, you should get an error message, and we'll talk about that soon. ln of 1 plus square root of 2, this is what you should get. Now on some calculators, especially if you don't have a line displaying what you're typing in, you may have to do 2 and then the square root button and then add 1 and then ln it. So just play around with it, and again, make sure that you're getting these answers. So the 4 properties of logarithms are also valid for natural properties. So again, I would write this down. I would say properties of natural logs. Properties of natural logs. First of all, ln of 1 is equal to 0, and that's because e to the 0 is 1. ln e equals 1, and that's because e to the first is equal to e. Very similar to what we noticed in the other properties. ln e to the x equals x. Notice ln e almost looks like a line, L-I-N-E, and so I'm just going to put a line through it, and I just get x. And then also e to the ln x, again, put a line through it, and you get x. And if ln x is equal to ln y, then x is equal to y. And this is your inverse property and your one-to-one property. Super important. We're going to use these a lot. So try out the questions, see what you can get by with, use the properties as you've seen here, and let me know if you have any questions.